The first two sections in Chapter 5 are really putting together a lot of the skills that we've learned in dealing with forces. So the first section is dealing with the naming of forces, and the naming convention that we've been using is we use force, the type of force as the first subscript on the target by the agent. And the types of forces that we've dealt with are the normal force, friction, gravity, tension, and electrostatic, and on occasion we've actually had magnetic forces as well. So those are the primary types of forces. We might also include spring in there, although spring and tension are essentially the same thing. And then the target is what the force is acting on. The agent is the object that's causing it. So these two things should be objects, and this target then tells you which free body diagram the force should show up on. So as usual, we have F grav on, say, block by Earth. And one of the reasons that I really emphasize writing down your system and your surroundings is that when you draw the free body diagram, your target is usually going to be your system, and the agent should appear in the surroundings. In fact, for every thing in the surroundings, it should appear on at least one of these forces. One of the first questions you really want to ask yourself when you look at pretty much any problem is the net force on the system zero? And if you know that, that really simplifies your steps quite a bit, because if the net force on the system is zero, you know several things. You know that the velocity is constant. You know that momentum is constant and conserved. You know that the sum of the forces is zero, so that gives you another piece of information. So this question should be really one of the first questions that you ask yourself when you face a problem. And a lot of times you have to go off of the description of the problem. For instance, if it talks about an object that's moving at a constant velocity, or moving in a straight line at a constant speed, or not moving at all, those are direct indications of the fact that the net force on the system is zero. So look for that piece of information when you get started. So I want to work through one of the examples in the book. This is the example on page 182, and you have a 3 kilogram block that's held up by a couple of strings, and I want to find out what the tension force in the two strings are. So I've already kind of set up the first few steps. I've got my sketch. My system is the block. The surroundings are the two strings and the earth. Here's my free body diagram for the block. And notice I've got, let's see, string 1, that appears here. String 2 in my surrounding appears here. And then the earth appears here. And I've specified clearly that the net force on the system in this case is zero. I've got my list of knowns, and then for my strategy, what I'm going to do is set up force vectors with variables for each force on the free body diagram. And then I'm going to go ahead and add those up and use the fact that the net force is zero, and then from that equation then I'm going to solve for the two tensions. Now the book tends to break things out into components. I prefer to leave things in vector format until we get to this stage right here, just because for me it makes more sense and it keeps things a little bit tighter, and you don't have to worry about keeping things straight quite as much. So let's go ahead, and typically when you write out these forces, you want to write out their magnitudes in terms of variables. So in the case of F10(1), I'm using that as an abbreviation for the tension on the block by string 1. So we just go ahead and we just write this as the magnitude of F10(1) times the unit vector. So I need to figure out my angles. Cosine theta x, that's the angle between the vector and the positive x-axis. So let me just set this up over here. Here's my x-axis, here's my y-axis, and then the vector goes off like that. this angle is 33 degrees. Incidentally, it turns out that is also my theta sub y. So theta sub x is this angle right here between the vector and the positive x-axis. So that's 33 plus 90, or 123. So we have the cosine of 123. That gives me the component of my unit vector in the x direction. Then for the y component, it's going to be cosine of this angle with respect to the y-axis, 33. And then the z-axis, well, if the z-axis is pointing straight out, that is a 90-degree angle. So that's going to be cosine of 90, which we know is also 0. So F10(2). And, at this point, we don't want to be guessing as to what these magnitudes are. That's why we just leave them as variables. We can solve for that later on. So tension 2 is along the x-axis. That's going to be cosine of 0. The angle with respect to the y-axis then is 90. And the angle with respect to the z-axis is also 90. Incidentally, cosine of 0 is just 1. These two are 0. So I could have just written down 1, 0, 0. Okay. And F grav. Now, since I know the magnitude of this force unequivocally, I'm just going to write down mg. I could write that down as F grav, but I'm just going to save myself a step. And I'm also going to go ahead and jump right to the vector. So this is 0. The angle between the vector that's downward and the y-axis is 180. The cosine of 180 is -1. We also know that it's pointing in the minus y direction, so that's where this is coming from. And then it's 90 degrees between the vector and the z-axis. That's going to give me another factor of 0. So that's my first step. I've set up the force vectors with variables. So the next step then is just to figure out what my net force is. And I'm just going to go ahead and just go down each of the components and add them up. So in the x component, I've got F10(1) cos 123 plus, let's see, the cosine of 0 is 1. So this is just F10(2), and that's a 0. So that doesn't give me anything. Now we do the same thing with the y component. F10(1) cos 33. Cosine of 90 is 0, so this contributes nothing. And then minus mg. In the z component, we get 0 plus 0 plus 0 is 0. So that doesn't help us. Incidentally, if these did have a z component, we would have another equation there to help us out. All right. So this is my net force, but I know that this is also equal to 0, 0, 0. And so now I'm going to break out the components and realize that each component here is actually equal to 0. So let me write out the x component first. We have F10(1) cos 123 plus F10(2). That's equal to 0. That's the x component. The y component then gives me F10(1) cos 33 minus mg equals 0. So I have two unknowns. I don't know what F10(1) is. I don't know what F10(2) is. I do know m. I do know g. I have all my angles. So two unknowns means I need at least two equations, which fortunately I have. So there's several ways to do this. Maybe the easiest way is to look right here. This equation only has one unknown, so let me solve it. And that's going to give me that F10(1) is equal to mg over cos 33. Now I can take and plug this value in for F10(1) in the other equation. So that gives me mg over cos 33 times the cosine of 123 plus f10 2 equals 0. So solving that, I get that f10 2 is equal to negative mg cos 123 over cos 33. And so now I have equations for both of my momenta, right? I'm sorry, for both of my components, right here and right there. Just to kind of check, we can see that if the mass of the object were to increase, both of these forces would increase, which is what you'd expect. Another thing to look at is if the angle with respect to the y-axis went to 0, what would end up happening to these two components? Well, if this angle went to 0, cos of 0 is 1, the tension in string 1 would just end up being mg. In other words, this thing would support all the weight, and hopefully, let's see, this would go to cosine of 90 over the cosine of 0, which would go to 0 over 1. This component would go to 0. So if that angle of that top string went to 0, all of the force would be supported by this weight, which is what we would want. So that's a good way of checking this, is looking at the angles. So in terms of checking, if theta y goes to 0, then f10 goes to mg over cos 0 equal to mg, and f10 goes to negative mg cos 90 over cos 0, which is equal to 0, which is what you would expect if the string 1 supported all the weight.